Thank you for the kind introduction. Today I'll be talking about low power, low noise, wide bandwidth MEMS accelerometers. Here's the outline of the talk. First, I'll go over a bunch of sensor interfaces that ADI offers. Then I'll talk about a technique to widen the bandwidth of MEMS accelerometers called beyond resonant frequency sensing. Then we'll go into the real ASIC design of that and some related measurement results. And then after that, we'll talk about an application where we can use wide bandwidth MEMS accelerometer. And finally, I will conclude the talk. So Analog Devices has a large portfolio of sensor interfaces. We develop technology to bridge the physical world to the digital world. Some of the sensor interfaces we offer include inertial MEMS sensors, temperature sensors. We've talked about that in this particular workshop. Biosensors, current sensors, electrochemical sensors, gesture time-of-flight sensors, magnetic field sensors, optical sensor sensing interfaces, RF transceivers. So I'm going to focus a little bit more on inertial MEMS sensors. We work on accelerometers, gyroscopes, and inertial measurement units, or IMUs. These find applications in different markets, different spaces. In the industrial space, vibration sensing enables modern smart factory where we sense vibrations to understand the machine health in real time. In terms of autonomous machines, we have them in agriculture to optimize productivity and efficiency. For automotive, we have automotive safety for airbags and electronic stability control, as well as cabin experience such as road noise cancellation to make the space quieter, more comfortable inside the cabin of a car. In terms of digital healthcare, we measure heart and lung sounds to understand and measure and record the patient's health. And in the consumer space, we work on, it finds its applications in augmented reality, true wireless stereo earbuds, as well as other wearables. There's an upcoming talk in June by my colleague Zeno to talk about sensors in digital healthcare at Hilton Head in 2024. So since we're going to focus on the accelerometers for this talk, I'll go over some basics. Accelerometer consists of a few parts: a proof mass that moves, a spring that's connecting to the proof mass and a fixed anchor point, and a differential capacitors that one side of the differential capacitor is connected to the proof mass that moves along with it. The other side is connected to fixed anchor points. Under acceleration, the mass moves, and this displacement changes the capacitors of a parallel plate capacitor, shown by this equation. And since there's a change in capacitance, we can measure that. The delta C is usually in the order of 1 femtofarad to 10 femtofarad per G. Now, if we can measure this change in capacitance, then we have a method to measure acceleration. Let's build an ASIC to measure this. Then we now have an accelerometer that can either read out acceleration in analog format, such as volts or milliamps, or we can do it in a digital format in bits. Notice that this spring mass system has a second order transfer function. The input is acceleration, the output is displacement, as shown here. And the other variables are damping factor, mass, effective spring constant, quality factor, and natural resonant frequency. And this second order transfer function has a resonance, which is quite important. Traditionally, when we make MEMS accelerometer real ASIC, we stay far away from this resonant frequency. This results in a narrow bandwidth of a MEMS accelerometer as a system. Now, how do we widen this frequency so that we can measure something that is frequency rich, such as audio or vibration in a system. One method is to increase the resonant frequency of the MEMS structure. But unfortunately, that decreases the SNR, so that does not help us to make a low noise wide bandwidth MEMS accelerometer. So what we're showing here in this talk is a circuit technique to widen the bandwidth of a MEMS accelerometer. Let's go over how that works. Let's start with a capacitive MEMS sensor design targeting for good noise performance and small form factor.
Sorry, can you please just speak directly into the microphone?
Oh, of course, yeah. Okay, so we start with the capacitive MEMS sensor design that's targeting for good noise performance and small form factor. Then we need to design a wide bandwidth analog front end that digitizes the full sensor response, including and beyond the resonance of the sensor. This means additional dynamic range. And once we have digitized all of that, we can now apply a digital equalizer based on the measured sensor response to try and compensate for the resonance of the sensor. And after all that, what we achieve is flatness for the entire signal chain response while maintaining a wide bandwidth. The details of that is covered in our JSSC paper. So let me summarize that for a bit. What we talked about is our high performance signal path, and we're using beyond resonant frequency sensing to sense and extend the bandwidth of the accelerometer. What we're doing here is we're digitizing the full response, including and beyond the sensor's resonance. And then once we have that digitized, we apply digital equalizer to restore the flatness of the signal transfer function. And this is capable of handling the full-scale acceleration input across the entire spectrum robustly. In our sensor, we also measure temperature, and to do that, we have a low-power signal path. Taking advantage of that, we also measure 3-axis accelerometer with a traditional bandwidth, where we tap the signal from the high-performance signal path and measure that simultaneously. This enables application to use both paths to toggle between the two, the high performance and the low power, in order to achieve a lower power consumption by duty cycling the two, or use both of them simultaneously. An example use case would be, for example, streaming music in an earbud or audio in an earbud using the high performance path and tracking the head or the body motion using the low power signal path. Another example is using the low power signal path as an activity detection to wake up a more power hungry circuit, for example, the high performance signal path or a microcontrollers. Now that we talked about the technique, the circuit technique of a beyond resonant frequency sensing, we can go a little bit deeper. Let's take a look at the architecture and the actual implementation itself. This slide shows a block diagram of the dual signal path architecture that simultaneously perform wideband acoustic or vibration sensing and lower bandwidth motion sensing. We have 3 identical 16-bit high-performance signal path on top, and then 1 shared 12-bit low-power signal path tapping from the high-performance signal path on the bottom. Along with it, we have other peripheral circuits like oscillator to excite the sensors, as well as LDO and temperature sensors and other digital circuits for communications. Let's focus on the high-performance signal path for now. Here's an overview of that. First, coming out of the sensor, we have a modulated signal, and to sense the charge coming out of it, we have a charge-sensitive amplifier configured in a capacitive feedback. To make sure that it has DC biasing on the input as well as output, we have switch capacitor resistors for DC biasing on the input and switch capacitors resistors for common mode feedback on the output side. Once we have after the charge sense amplifier, we have demodulation and anti-aliasing filter before we go into ADC driver that transfer the signal into a second order delta sigma ADC. Here we have a discrete time second order delta sigma with a 4-bit SAR ADC as its quantizer. The choice of a second order delta sigma as an architecture is due to its capability to handle large input signal. And this is particularly important in our application because we're using beyond resonant frequency sensing. So we're expecting a gain from the mechanical side about 1.5 to 5 coming in. So then we need to accommodate for such large input signal without going to instability. The output of the delta sigma ADC here is a 4-bit bit stream that goes into a digital filter. The 4-bit bit streams are decimated to a lower rate for low power operation and then equalized and going through another set of low pass filter for the final output data rate. The equalizer on chip is based on measure resonant frequency and quality factor at test. So every chip is customized to have its own EQ coefficients to make sure that the flatness response is maintained for every single part. So the sensor characteristics, as I mentioned, are measured at test. How are we doing this? We're using ring down measurement technique with electrostatic actuation. Basically, we apply a voltage to move the beam and let it relax to see how it rings down. And from that, we can capture the resonant frequency as well as a quality factor of the MEMS sensor for every single part of test. Using the measure F9Q, we go through a lookup table that is pre-populated, shown in this plot in a cartoon picture where we're covering a variety of sensor characteristic, and we just plug in those numbers for the coefficient. And in the end, we get a response that is flat based on the measure F9Q. Now let's go a little bit deeper into the actual circuits. Let's talk about the charge-sensitive amplifier first. As mentioned earlier, the MEMS sensor capacitance changes with respect to acceleration. So how do we measure this change in capacitance? We apply a known voltage, excitation voltage here, and then we measure the output charge that comes out of the sensor using our CSA. If all the capacitors are balanced, for example, no acceleration, then there's no charge that comes out from our excitation. If the capacitors are not balanced due to excitation, then once we excite the capacitors, some charge will come out and we sense that change in capacitance, we sense that charge to know the change in capacitance. And that's how we measure change in capacitance. The CSA is configured as an amplifier with capacitive feedback to sense this modulated signal at an excitation frequency of around 64 kilohertz. As I mentioned earlier, we use switch capacitor resistors for DC biasing. How this works is that, so using switch capacitor resistors for DC biasing. And some of the design factors are we can choose the size of the capacitors. We can choose the sampling frequency of the switches. The choice of the capacitor affects the transient settling response of this DC biasing. And if it's too large, it also has larger alias noise charge coming back to the input. So we need to choose that carefully. We also choose a sampling frequency here to create a notch at where the modulated acceleration signal resides. So by doing that, we can minimize the amount of noise alias back to our band of interest. And to make sure our DC biasing is signal independent, we use two capacitors, sampling at 180 degrees apart. So that's the two phases of the modulated signal. And once we sum that together and bring it back into the input, the signal content is canceled out, so we only have the DC content, the DC biasing. So let's put that all together. We have switch capacitor resistors for DC biasing on the input side. We place a notch right around our excitation frequency where the acceleration signal resides, or the modulated cell signal resides. And once we demodulate that back to DC, the noise is dominated by the amplifier. In terms of the common mode feedback, this is also implemented using traditional switch capacitor resistors. And to make sure that we can account for the MEMS sensor's offset, we cancel that out with a capacitive DAC that is injecting charge at the same modulation frequency as our excitation voltage. So that looks just like an offset, and we cancel that out using a capacitive CDAC. The amplifier here is implemented as a classical two-stage amplifier with Miller compensation. Now after that, the signal gets demodulated and ATLS filter, and then driven from ADC driver into a delta sigma ADC. Here we have the schematic of the second order multi-bit delta sigma modulator. This modulator consists of two pseudo differential switch inverter based integrator. Here we have the stage 1 on the far left and stage 2 in the middle here. And a self-timed 4-bit SAR ADC quantizer, which is shown here with some digital logic in the bottom here. First, let's take a look at the self-timed SAR quantizer. This SAR quantizer includes a mid-thread transfer function to minimize coactivity under zero acceleration. So when two of the axes, if it's placed on the table, is most of the time zero, so we want to minimize the co-chattering at that point. It also does an important job of generating asynchronous timing for itself, as well as the non-overlap clocking required for the delta sigma modulator. This makes, at the chip level, this makes the timing easier. The SAR ADC also performs summation using the capacitors to realize the transfer function required by the delta sigma modulator. We can see that by changing the weighting of the capacitor in blue, red, and green, we can do the necessary summation in order to realize the second order transfer function for the delta sigma modulator. Going to the amplifier a little bit, here we're using differential inverter-based amplifier for its low power characteristic as well as its wide output swing. The integrator features two phases: the sampling phase, where the input signal as well as the bias voltage are sampled, and then an integration phase where we apply double sampling to increase the signal amplitude. To make sure that the power consumption of the delta sigma modulator is it's appropriate for the mode or the sampling frequency, we implemented a slice programmable amplifier in the first stage. This offers a speed power trade-off to enable more scalable current for the delta sigma modulator. On the left, we have a schematic of one fixed amplifier slice with 7 additional slices that, depending on how you operate the chip, it will enable the slices necessary. On the right-hand side, we have a simulation result showing that depending on the sampling frequency of the MEMS accelerometer, or the output rather, we have different current. This is the sampling frequency of the delta sigma modulator, really. Moving on to the low power signal path. The low power signal path digitizes on-chip temperature sensor and also captures the low bandwidth 3-axis acceleration signals. We have a dedicated temperature sensor on chip that is digitized using a SAR ADC, as well as tapping into high performance signal path and digitize the motion part of the acceleration using the SAR ADC. Now that we cover all the design aspect of it, let's take a look at the silicon results. On this slide, we're showing the FFT of one of our prototypes, the 8G accelerometer. On the left-hand side, we have 1G acceleration at around 1 kilohertz, and on the right-hand side, we have the same acceleration around 3.6 kilohertz using a mechanical shaker. We can see that at 1 kilohertz, the signals are, the digital equalization are not affecting the signals. And once we go into a higher frequency where the mechanical gain is gaining up the unequalized signal, as we apply EQ, it compensates for that accordingly. On a different prototype using the same ASIC, a 30G accelerometer, we're also observing the same thing. We apply a 4G acceleration at 1 kilohertz, and we can see that the signal at 1 kilohertz look as expected, and moving the frequency of that same signal to 7.6 kilohertz, we can see that an unequalized version has a mechanical gain, and once we equalize that back, it comes down to the expected level. I just want to note that on the low frequency, there's a bunch of tones here. These are due to the electrical and acoustic environmental noise in the mechanical shaker lab. There are a lot of different machines that's running at the same time, and also different humming, so that we capture that as part of our evaluation. It's very difficult to isolate a mechanical shaker with a clean, noiseless environment. On this slide, we're sweeping the tones across the different frequency in the spectrum. And for the 8G accelerometer, we can see that without EQ, we can see the sensory response. There's a mechanical gain, gaining up this acceleration, the digitized acceleration signal. And once we equalize that, now we have a very flat response, just like how we want it. And making sure that this technique works for different parts, we try out 4 different parts on the slide. And since we have the measure F0 and Q numbers from a test, we can apply different EQ coefficients. And the end result is that we can flatten out all of them into I think it's plus or minus half dB level. We did the same thing with our 30G accelerometer prototype, and we observed the same thing. By applying EQ, we can flatten out the response here through all 3 axes. And across different parts, we can maintain a flat response up to 7.6 kilohertz. This slide shows the delta sigma modulator's noise and harmonic distortion. Here we're measuring just the ADC driver, delta sigma modulator, as well as a digital filter. And for the 8G accelerometer prototype, we find that the noise is about 9 dB below the total MEMS accelerometer noise. In terms of the third order harmonic, we're observing 98 dB below the fundamental, which is sufficient for an accelerometer. As for the 30G prototype, we find that the total noise from the ADC driver, delta sigma modulator, as well as the digital filter is about 4.5 dB below the total MEMS accelerometer noise target, and that the third order harmonic distortion is about 95 dB below the fundamental. Here we have a noise measurement of the 8G prototype, and this is now in a very different environment where it's on the Airtable, everything's quiet. We make sure that there's there's no signals, acceleration signals around, and we cover it to make sure that we also don't pick up acoustic signals. For the AG prototype, we're seeing about 25 microG on the X and Y axis, and then around 30 microG on the Z axis. Similarly, for the 30G accelerometer prototype, we also check its noise performance, make sure everything looks good. And for the 3 axis, is all about 16 microG per root hertz. One interesting thing to know is that the EQ suppresses the ASIC noise around the sensor resonant frequency. This is particularly obvious in the 30G prototype in the Z-axis. We can see a dip here. On this slide, I'm showing the root Allen variance plots of the 2 accelerometers. The in-run bias stability is about 1.5 microG and 8.5 microG for the 2 prototypes. And throughout the chip, we're using one of the F noise mitigation techniques to try and minimize the contribution from the ASIC. And looking at the data, we suspect the limiting factor is due to the long-term stress from the overmold package that is limiting our measured in-run bias stability. And what this means is the offset drift over time. In terms of the power consumption, this slide shows the current consumption. The accelerometer real ASIC is designed to have most scalable current, so we can see that depending on the mode selected, we can have different current consumption. And the signal chain accounts for about 90% of the current consumption. And if we enable the dual signal path feature, this will increase the total current by about 5 microamps. To illustrate the flexibility of the digital equalizer, on this slide we're showing by reconfiguring the EQ coefficients, we can extend the bandwidth of the MEMS accelerometer to beyond the resonant frequency. So here, with the standard EQ coefficients that we're running, we get 4 kilohertz bandwidth, and then we can double that by reconfiguring it, and that is beyond where the sensor resonance is, which is about 4.9 kilohertz for this particular sensor. Similarly, for the 30G sensor, which typically has a 8 kilohertz bandwidth, we can double that up to about 16 kilohertz if we reconfigure the equalizer. Here's a chip photo showing the MEMS accelerometer. On the left-hand side, we can see that the MEMS sensor is on top of the ASIC with bond wire connecting to the ASIC and then eventually to the package. On the right-hand side, we have the photo of the ASIC. It's implementing 0.18 CMOS and occupies 2.17 millimeter by 2.32 millimeters. Here we can also see 3 high-performance signal paths and 1 shared low-power signal path. Here's a performance summary of our prototypes, and it achieves low noise, wide bandwidth, while maintaining competitive energy efficiency. Now that we talked about the MEMS accelerometer design and the measurement results, let's talk about how we can use this in an application. In a smart factory today, it's important to measure the health of the machine in real time. For example, measuring the vibration, the power consumption, the temperature of the machine, as well as maybe some noise that's in the audio range. And this is condition-based monitoring, or CBM. And if we use all these different sensors along with some algorithm like machine learning, AI, analytics to predict when the machine might fail in order to optimize operation, for example, have a part replacement order in place or schedule downtime for maintenance or change how the machine is used in real time to extend the useful life of the machine. That is a predictive maintenance, PDM. And vibration sensing is a key part of condition-based monitoring in order to understand how healthy a machine is or at what level the health is at. Let's go through a hypothetical example. In this case, I'm using a motor as an example here. So on the factory floor, a new motor is ordered and installed. It's installed professionally. Everything looks perfect. It's under warranty. It's running smoothly. And a couple years goes by. Now the warranty has expired, but we're still doing the regular maintenance. So that the machine is running pretty much as new. Everything's in spec. Everything looks good since we're doing all the required maintenance on a regular basis. So everything looks good. And then a couple more years goes by. Out of nowhere, a random event, for example, a particularly cold night or a particularly hot day, there's a fault that has occurred. But this is very, very, very minor. It's maybe it has a subtle vibration. Maybe it's not really. Everything's in spec. You can't really notice that the fault has happened. So the machine keeps running for months and months. This tiny little fault gets a little bit worse. Now the power consumption, it's up a little bit because the machine isn't as smooth, but everything's still looking okay. The machine is still doing its job. It's running along. And if we let the fault get worse and worse, now the temperature is starting to pick up because it isn't running as smooth. But maybe it is still doing its job. So then a couple more months goes by. Now the machine is really running a little bit rough. You can hear the noise. There's audible signal. And at this point in time, we're probably weeks away from a likely motor failure. So in this particular case, if we can sense the vibration here, we have early signs of when something might have gone wrong, and then we can then start to look at what could be done to help the operation there. So in that example, we notice that low noise wide bandwidth accelerometer can help us reveal early signs of a fault, and this can happen while the machine is continuously running. It doesn't affect the actual machine operation, and the detection. I guess I just said that, detection of the mechanical fault while the motors are still running. So that is extremely helpful. We can, in real time, sense what kind of vibration is going on. Is it an expected vibration, or is it something that is a little bit different from before? Maybe a very, very small fault that the output of the machine is still correct, but it's not running as smooth anymore. Now continuing with the same example, same hypothetical example of a motor fault. Here's a study showing that bearings contribute the largest percentage of the motor fault, is 41%, while all the other 4 failure modes only contribute 59%. So if we can understand how a bearing fault happens, that's a very good path to understanding the machine health. And bearings are used very widely in the industrial space. Let's go through an example of detecting emerging fault in a bearing. So here we have a very small fault in the bearing. We can detect a subtle vibration that has high frequency and low amplitude. And as the fault gets worse and worse, the magnitude increase, and the frequency may become lower now. And as the fault gets worse and worse, the machine becomes noisy and noisier. We can see that the noise floor has picked up, and that we have a low frequency fault frequency as well as a largest magnitude here. So using this example, it's particularly important to have a low noise, wide bandwidth accelerometer to understand when the fault has occurred, and also to be able to track that as it goes, as the fault becomes worse, to understand how to deal with this fault in the machine. Now that we talked about the bearing a little bit, here are some other examples of faults that vibration sensing can help identify. This include imbalance, misalignment, bearing defects, and gear defects. And by having a low noise, wide bandwidth accelerometer, we can help identify these problems. So in this talk, we talked about world's first 3-axis capacitive MEMS accelerometer, real ASIC, using beyond resonant frequency sensing. By doing that, we can achieve energy efficient, low noise, wide bandwidth accelerometer. We can extend the bandwidth to near and beyond the resonant frequency of the sensor. And we can robustly sense a full-scale acceleration signal across the entire spectrum. We also touched on dual signal path that enables flexibility in sensing frequency-rich and conventional acceleration signals. The wide bandwidth signal path can sense something like acoustic or vibration, and the conventional signal path can sense motion. And both of these can be used simultaneously as well. And finally, I touched on an industrial application where a low noise, wide bandwidth accelerometer could be helpful. Here are some references. Thank you very much.